Has anyone used the Zoom, the YouTube videos, or you have? All right, so they're working. Okay. That's good.
Your YouTube videos?
Yeah,
Yeah.
right. That's good. You never know. I mean, you kind of put things up, and then when I glance at it to see if it linked up, but let's see. There's this business. Let me get that. This homework. Systems. Oh, the homework. Like that. I didn't want homework one. Two. Some of the papers here. All right, so it's the one. That's not the one. This is the one. So it asks you to derive that. So I'll go through that a little bit. Anyway, so let me get back to the. Any questions? Anything? Oh, I know. Last time someone came up and asked about this. Oh, this business. So he goes through this. Right? He goes through this and he says the second order, the Neely temperature is supposed for anti-ferromagnetic to parent magnetic. So you have, where's our picture of the magnets? So here, right? So you have ferromagnetic, the thing's magnetic, right? And then if you heat it up, it goes to paramagnetic. There's something that if you put a magnetic field on it, it becomes a magnet, like steel or something, right? Put a magnetic field on it, it becomes magnetic. When you cool it down, it'll go to this ferromagnetism or it's stuck in a magnetic state for the directors. The magnetic field orientation all going in the same direction. So like north-south pole. I guess I started a little bit early, but anyway, so that's a first order transition, right? And then they, I guess somebody discovered, I'm not an expert in magnetism, but somebody discovered this ferromagnetism and anti-ferromagnetism, where you have this thing would be non-magnetic because it's got perfectly matched kind of up and down domains. And this one's magnetic, right? Because it's got majority one direction, but has some pointing in the other direction. Right, so this would be like special alloys where you have domains of different magnetic orientation in it for whatever reason. Right? So some of the reasons why this happened, I think, aren't necessarily understood. Right. So it's just a kind of a cartoon, and these things aren't atoms, they're like domains, like micron, kind of like a fifth of the diameter of a hair, something like that. 10 micron things, 5 micron, like, so they aren't at atomic level domains, right? So you can see these things with neutrons, because neutrons have a magnetic moment. So like a neutron beam, get from a nuclear reactor, and shoot it through these materials, and you see these domains with a neutron beam because they interact with the magnetic fields, right? So there are ways to like kind of observe these domains, but in a sense, they're just like a construction. But and especially when you say like the Landau theory, you're going to use it for phase separation for composition. You're going to swap out this magnetic director with the composition. You're going to say like you're still going to have order of like they're going to have a first order phase separation that has a heat of demixing, but instead of this director arrow thing, you're going to have like the composition replaces that. Things get to be weird, right? So you can kind of replace this arrow thing with a lot of different things, but the original development of transition under the theory of transitions started with magnetism. So you kind of have to look at that first, even though it's something you may never deal with, right, at all. So, I mean, there is quite a bit like microelectronics and in like memory storage, things like that. So this is an important field, but it isn't like such a dominant field, I guess. So even within materials, it's going to be like maybe less than 1/10 of the people work in this area. So it's a foundation for the thermodynamic understanding of transitions. So that's why we're looking at it. Anyway, so that's a first order transition, and this is generally deemed transitioning from this to paramagnetic, like ordered to disordered from ferrimagnetism is generally considered to be a second order transition. Okay, so in the paper, so this guy in that book, he says like these iron oxides are like kind of a classic example of second order transition, but then he shows this plot, which is from his paper. This is from, see, this isn't the updated version of this because they put his citation in this. Let me see if I can get the right version of this. These slides. Let me close this. This is slide 18. Let's see. This should have been updated. And this should be the updated one. No. Third version of it. Slide 18. This. All right. Anyway, this reference 19 is Dolan, the guy that wrote the book. Right. So he's referencing his own paper. Oh, but the other slides aren't here. So this thing wasn't updated. All right. Well, anyway, I put the it's under the components. I put the paper up here somewhere. First order magnetic. Okay, so this is a more recent paper. That paper, that reference 19 was like, I don't know, it was from 10 years ago, something like that. So this is from 2021, right? So it's kind of more recent. They're also saying that this antiferromagnetic to paramagnetic transition should be second order, and they're saying there's a nuance in a certain system, right? And they go through the magnetic susceptibility, which we don't really need to talk about right now. Anyway, finally they get this plot, which is the same plot as what he has in the book, and they're saying this demonstrates that it's a first order transition. All right, so notice it's like, I mean, just to take a glance, you can compare these 1 to 1, but basically there's like a little bit of a skewed kind of Gaussian spike, right? And then in our thing, it's exactly the same thing. Like it's a little bit skewed Gaussian spike. In that paper, right? So this paper is in some like not well-cited journal, like a decent journal, but not well-cited. And that one, this thing is in PNAC, which is Proceeds in National Academy of Sciences, which is kind of like if science, nature, then nature has a bunch of different nature materials, nature bio, whatever. So nature has a bunch of different branched off journals. Those are all have a citation index, like the average citation for a paper in nature is something like 100. And the average citation for a paper in this reference 19 is probably like 3. So, and the average citation for the PNAS is it's probably the same. It's like 150 or 100, some huge number, right? So this is National Academy of Sciences. So anyway, this is a good journal. This is like one of the top 3 journals probably, but it's not as high as Nature and Science. Anyway, so he's saying this is what he's showing. So it's the same thing. That's the bottom line. So that's a first order transition, right? I mean, that's the signature of a first order. Why our book guy is saying this is second order may have to do with some kind of internal mental conflict he's having here. I mean, maybe, so he's convinced himself that this is second order, but he shows the data that shows it's first order. So then he says it's an example of a second order. I think that this, so if you look at the 0.947, that one kind of looks like it's a second order, like you have a CP and then there's a kind of a discrete transition to another CP. So that could be, you could say that's second order. But this one, the dominant one in the plot seems to show it's a first order. So he also goes through this methods of describing how you get this peak, like how you can model it with this ended model, which is based on this the Landau theory. So the Landau theory is a way to describe first order and second order transitions, right? So and it's where the terms first order and second order came from, and it has to do with magnetism. So first order, like you're going to run into it, usually it'll be like melting, like the fusion is a first order transition, the glass transition is a second order. Those are like the classic examples. In the world of magnetism, classic examples are ferromagnetic to paramagnetic first order, paramagnetic to paramagnetic second order. Those like their standard bearer things, So that because the theory was developed around that. So if you can find it, that's why that's a PNAC article, because you find a ferrimagnetic to paramagnetic that isn't second order, then that's kind of like news, right? Whereas this is kind of verifying the already known that this should be second order, except his evidence shows that it's first order, but he doesn't go out and say it because that would be sticking his neck out. And so sometimes things happen, I guess, and then it ends up in the book because this is his paper, so he puts it in the book. So I can't explain that otherwise. That's the way I understand it, Anyway, so this Landau was Nobel laureate, and he kind of won it for his first order, second order stuff, right? So, and he invented the hydrogen bond for the Russians, which wasn't such a good thing, I guess, from our perspective. So anyway, so the idea is this: so you have PVT. So you have like you can break apart the free energy into pressure, volume derivatives, and then in a system like this, then you're going to say, well, there's this other thing that isn't pressure, volume, or temperature. It's like the order of the system, like how ordered it is. So you can have another parameter other than pressure, volume, temperature, the order, right? So this gamma is so gamma is like small gamma is like the squiggly thing, and then capital gamma is this upside down L thing, right? So anyway, that gamma is the order parameter. So Landau said like you could do a power series for this order parameter. You could describe the free energy in terms of the power series. This is also, our book gives it this way, like this. And then, but the main thing from Landau is that this is an even, only the even terms matter in this, because somehow it has to have symmetry about the critical point. And you can't have symmetry with a linear or odd powered terms because a plus and minus would matter. So anyway, this is how our book gives it, and how other people give it is like this. Like you only have the even ordered terms, which I think this is probably an easier way to understand this. So you just have the even ordered terms in this order parameter. If you're in this disordered state, that order parameter is 0. If you're in this ordered state, it's going to be something bigger than 0. Like it's going to have a larger value. So anyway, so the free energy is going to be a power series, only the even powers, and you can take the first two terms. Then the first term changes sign at the transition. So the first term is going to be, I fixed this too. Right, it should be T minus TC, so that this term becomes negative when you're below TC. I don't know why I don't have the new version up here, but I have it on my computer, but anyway, it's too late for that. So all these places where it says TC minus T, that should be T minus TC. I think that also came from the book, but so it has to be that way because this term has to go negative when you go below this critical temperature. All right, so when you're above the critical temperature, this term is positive, so T is bigger than TC, and then this term B is always positive. So then this free energy is always the change in free energy on the transition. It was the transition meaning going from ferromagnetic to paramagnetic, or I guess this is actually going from, because the beginning first thing that he did was to define a second order transition. It's actually ferrimagnetic to paramagnetic. That's what he was talking about. So anyway, you can make it to be ferro to para, like the first order also. That's kind of the second slide here, but the first slide is the second order, like the second order, which would be ferry to para. So anyway, so this thing would change sign. So if this thing, if the change in free energy going from ferri to para, if this is above this critical temperature, then delta is always positive. So it always drives it so that the only answer, you always want to have a negative change in free energy. Like you have to reduce the free energy for the system to be happy. If the free energy goes up, it won't happen. Thing won't happen. So it won't phase separate, right? So if you're above the critical temperature, it's going to remain paramagnetic with all the arrows pointing in odd directions. This may be confusing, I guess. But so the idea is you have a transition where you have to have a rule where the free energy can drop when you go to drive the transition. The transition will happen if the free energy drops, and it's going to find a magic gamma value or its order value where it's happy. Right? In order to get that, this term has to be negative, that term has to be positive, then it's going to drop. And eventually this term has a higher power of this gamma. So as the order gets higher and higher, then this positive term will dominate, then it goes back up. Right? So you have a minimum because initially at small gamma, this term dominates, it's negative below the critical temperature. And then as you get to high gamma, high order, this term dominates and goes positive. So it leads to a minimum.
How can you explain how can we get the value of A and B?
At the beginning, this is just hypothetical, right? But so you know, because you can solve for what this magic gamma is, this gamma naught, the magic point where it reaches a minimum. So it's some temperature below the critical temperature. So you can measure that order value. So that order value you can get from a there's a mathematical way to get the order value. It's basically not that hard, but it's not that important either here.
And may I confused the difference A and A0? What's
A0 is at this magic value. So above the critical temperature, any kind of change in order will drive you to zero order. Like zero order is the lowest value, and at that point, the change in free energy is zero. So because your transitions from paramagnetic to paramagnetic, there's no change in free energy.
Yeah.
So then you have the magic order value be zero there. Then you reach this critical temperature, then the game changes because this term is negative and that term is positive, then you can have a minimum. And that minimum changes with temperature.
And the meaning that there is a A0 means the A is continuously difference between along the transition.
A0 is a fixed value. This A term would be a temperature dependent term, and B is not temperature dependent. So B is always B0. It's a fixed value positive. It's just a model to impose on nature. There isn't any basis for this. It's a Taylor series expansion, just a power series expansion. And it's just being imposed on an observation. The observation is that it's random, there's no magnetism, and then you cool it down, and then you get this forced magnetism. I mean, you could have magnetism here if you put a field on it and oriented the directors, right? But they're random, and then you cool it down, it reaches a magic temperature where they lock up, and then it becomes a magnet. So that's the Curie temperature. So ferromagnetic to paramagnetic is the Neal temperature. If it's ferrimagnetic to the second order one. And this is describing the second order one because you can start doing derivatives of the free energy. So the free energy itself is continuous through this transition. Right? The free energy itself doesn't show a step because you have a value right above when it reaches T0, this term just goes to zero. TC, this term just goes to zero, and then you just have B. And above it, it has a continuous value. So there's no discrete change in this. It's a second order transition. This thing is continuous through the critical point. There's no step of the free energy. And so anyway, the first derivative though has a step. So you take the derivative of this thing and you get this expression, and you can solve for this gamma naught from that. It's going to be a ratio of the A0 to B0s in this thing. And you can solve for this thing. And also there's this derivative of the free energy shows the step function. So basically from our square, so you can get dH is VdP, TdS. Right, so that's our fundamental equation. and then Cp is going to be dH dt at constant P, so it's going to be ds dt at constant P, because the constant P drops that term out. And so you have the S term defined in terms of Cp. And then G is F, so G is HST minus ST. Right? And then you can do this derivative of the free energy, which is the thing we had. It's this expression, so that's CP, it's got CP in it, it's got CV in it, and then it's got S in it from that expansion of this thing, derivative of that thing. And then the second derivative of this thing is just going to be Cp by T. So you can take the second derivative of that, get Cp by T, which is going to be this Cp by T, and then you plug in what we had for the definition of the free energy, and then so then you can solve, because you can get the second derivative of this thing, you can solve for Cp in terms of gamma, and you find out that that thing is going to linearly increase, and then basically when it reaches this critical temperature, it drops to 0. So basically that framework with these derivatives can give you the second order transition. The first derivative of the state function shows a discrete transition, and the state function itself is just continuous. In other words, it's got this weird shape to it, but it basically just, there's no step in it. It just goes to 0 and that's it. And it goes on. Right. So then Landau called this a second order transition because of the behavior of it. And then, so afterwards, and it matched with this ferroelectric paramagnetic transition. So the reason to go through this is because this is expanded then to, like, when you have a binary mixture of things and the composition becomes the order parameter. And then you can put in also electric fields instead of magnetic fields. You have electrical transitions, first and second order. So this is the basis on which all the other kind of understanding of order, first order, second order, came from. You know, the actual magnetic meaning is kind of a nuanced field. It isn't necessarily like the parent field. So that's how things work out. So there's several ways to get first order out of that model. Right? And so let's see. So you write an expression where you have this also should be T0 minus T. Not, so these are also all backwards. I fixed this, but somehow it didn't fix it on the web page. I loaded it over there, but I don't see exactly why it didn't. But so this should be T naught minus T, not T minus T naught. So see, this is the same thing as before, but there's a third term, the C term here. Let's see. So with this arrangement, we expand to the next even order term. It allows you to have this discrete transition, not at T naught, but at a different temperature here. So let's see how this works. A is the same term. T naught is the temperature, some temperature where A changes sign, not the critical temperature. And all these things are positive and constant. And then you do the derivatives of this thing. T greater than T naught, then you're in the paramagnetic condition. And then delta F increases for all gamma. So the minimum of that thing is at gamma equals 0, meaning that you have no order, meaning it's paramagnetic. And when T is less than T naught, F decreases from gamma equals 0 to a minimum at gamma, our magic gamma, and delta F is less than 0, so you're going to this minimum, just like before. And then B and C just add together. But when T is slightly bigger than T naught, delta F decreases in discontinuously drops to 0 at t star, at some other t star. So because you have this other 6th order term, the slope of this thing has a step function. So to find that step function thing, you set delta F equals 0, and then you solve this equation for a temperature above the T naught. So a temperature below the T naught. So dF dt equals 0. Set dF d gamma at 0. Let's see, I don't remember how to do this. Yeah.
You can show it on the board.
Yeah, I could, but I don't remember exactly how to do this. I did it last night, but I don't remember how I did it. So I can't do it on the board. The first derivative of t is discontinuous. All right, I just can't do it right now. Like my brain's jumbled on this. I'll do it next time. It's probably the best bet. But anyway, adding this other term allows you to get a first order transition out of this. I'll have to just do it next time. Yeah, I can't do it right now. All right, so you just have to live with that. All right, so then for this homework, let's see, you don't actually need this for this homework. This is just defining first and second order transition. The business of the all right, so the homework does involve this compressibility factor. Okay, so you have PV RT, so that ideal gas law. So if you take PV divided by RT, it defines this compressibility factor Z. Right, so Z is 1 is the ideal gas. Right, so in the homework, go to that. So it's going to use this compressibility factor. Here, this paper. Just talking about the Clath rates, I mentioned that before. And then, oops. I did something like, that's really weird. Oh, because it was stuck over there and it's blowing up this thing is messing me up. Yes, somewhere there's a plus here. That's all right, so just got this equation, which is like the Clausius-Clapeyron equation that we had. This equation 2. So except it has this Z in it. All right, so we did this. So we did that. We didn't have any Z, right? We just have delta H. Sorry. We just have let's see, the 1 over T version. Ln of P versus 1 over T is delta H over R. Right. So that's our thing. And then his thing, it's got delta H over R of Z. Right. So the question is, one of the questions here is like, where did equation 2 is like what we had, what's this thing Z in here? Right. So you can write so if you just write out, I think what you can do is just say so it's got, let's see, before that he's got V here in the previous thing. RT, so you have V here, like the Clapeyron equation, you have V. So you could say like if right, come on. Clapeyron was dP dT's delta H over the transition temperature and this V, and then you're going to substitute in V vapor for delta V because this liquid is much smaller than the vapor. Then you're going to substitute in that V equals like RT over P. Right, and then that gives you dP over P is ln P, and then dt over T squared is d1 over T. And then dP over P is d ln P. This is like just normal thermo, like these are used like over and over again in thermo, like those substitutions. So it might look new to you, but this is like just standard how stuff is done there. Anyway, so then if you say that if you do accept that substitution, and then you say that Z is PV over RT, then you can say that that V here, V is going to be Z RT over P, right? And then you can just kind of plug that in here, and you'll get ZR. You still use the T squared and the P to get to do these things. We end up with ZR as the term, right? So that's kind of simple to do if you figure it out. You're just going to plug that in, you get ZR instead of R. And so Z, the reason we do that is if you want to have non-ideal, then you can calculate the Z. Like for non-ideal, you can just calculate it in terms of Z, this compressibility factor. Right, so you can use, so to get Z, in other words, you could, all right, let me go back to that. It's like you can use, instead of PV is RT, then you can say, so P is RT over V, then you can include the van der Waals modification, like minus B minus RT over V minus B minus A squared over V squared. So in other words, rho squared is 1 over V squared. So it's like this is binary interactions, attractive interactions that allows you to have a liquid state. Right? This is excluded volume, like it reduces the volume, increases the pressure. This decreases the pressure. Right. So then you could take this equation and write an expression for Z in terms of like a function of A and B. Right. So Z isn't 1 anymore, it's some function of A and B. Right. Just I don't remember the exact function, but it's in the notes what the exact function is. But anyway, so that means that because you have this Clausius-Clapeyron written in terms of Z, then you can use a non-ideal gas. You can use a van der Waals gas, this non-ideal, and include it into the same Clausius-Clapeyron equation. So like expands it significantly. Allows you to talk about real gases instead of ideal gases. Right, so that's kind of the idea of this thing. And there's other equations. In particular, for these kind of gases, like simple gases, then you're going to use, see, high fluorine controls. Actually, I need one more of these. Let's see if I have. So you can use this Peng-Robeson equation of state, which is like the van der Waals equation of state, but it's better. Like it's just an improved version, empirically improved. Right? And these guys were, I think they were Canadians. So there's many equations of states. So you can pick and choose which one you want. But this is the most popular one in the petrochemical industry. So for gases like CO2, methane, propane, whatever. Right. So if they're dealing with like trapping hydrogen, CO2, this is the perfect equation of state to use for that stuff. Okay, so anyway, so there's from the undergrad chemical engineering book, there's an Excel sheet where you can just get that number if you want. I think I just downloaded it. It's an Excel sheet, so I can show you how to use that. So it's pretty simple there's gonna be like a reference state. So you're always gonna say enthalpy with reference to some state, because you can't get an absolute value for enthalpy or free energy. So you need to have a reference state for it. So you just say what so 0.1 megapascals in atmosphere, roughly 298 is the happy temperature. And then say you want to look at CO2, right? So this is set up for propane. So it's going to need, it's based on the ideal gas, so to get the heat capacity, usually you talk about an ideal gas heat capacity. So if you want to do CO2, it's somewhere at the bottom here. Gases, carbon dioxide. So those are the ideal gas heat capacity numbers. Now it's a power series expansion in temperature. So it starts out with a number, then temperature, and temperature squared, temperature cubed, goes up to temperature fourth power. Then it gives you pretty much the exact heat capacity for an ideal gas CO2. And this so it's going to calculate your value of CO2 Z, compressibility factor, by taking the conditions where you are, and then taking it through a transform to get to the ideal gas condition, doing the transform to get where you are from the reference state to where you are in temperature and pressure in the ideal state, which you have all the equations to do that transform, and then bringing you back to the reality with like a reverse transfer function. So that's kind of how it operates, this program operates. So in order to do that, you need the ideal gas heat capacity, and then you need to know, it bases all these transforms on the critical properties. So in other words, at the critical point of CO2, so you can get those numbers too from here. So those are the input values, like what is the critical values, TC, PC, and then the density of the critical state. And then so these are all like TC, PC, and omega it needs. This is a compressibility factor at the critical point. We don't need that. So right now, so I can go into the reference state and put in the values. So this is for CO2. I had the heat capacity numbers. They go into the properties thing. Heat capacity values I have A, B, C, D. Pesos. You need to protected you, but careful for enable editing. That's it. Right. So here you're pasting that isn't the same size. Should be. Oh, okay. Undo that. The ideal gas CP I have here. Let me highlight it here. CO2, carbon dioxide. We'll need to do this in some other homework, not this one, but so copy those values. Let me just do this my own sanity. Paste those in here. And then get the critical properties. Jump here. Carbon dioxide. And put those into here. And then everything changes here. Then you have to set whatever reference state you want. It's set for 298. You see this changed like already, 298.1, and then on that condition, so the cubic equation is going to have 3 roots, right? Unless it's supercritical, right? So in this case, it's got just the one root here, which makes it look like it's supercritical, which it isn't. Something's wrong with this picture. All right, this thing will calculate for you. But it should be, this answer has to be 3 here. Must have real values. So I'm not sure why that came out that way. But then you can get like at 10 atmospheres, what's the Z value for carbon dioxide? So you can find out. So it would have an equilibrium at some other higher pressure, like maybe 10 megapascals. Like at some point it'll have a root where it's got some value. Where it'll have like, this would be like liquid and vapor and equilibrium. You get the values for the enthalpy, all the values for the stuff, right? But so you can get the Z value. anyway, in this paper, he uses this kind of program. He uses this Payne-Robinson equation to get the Z value for the paper. When he presents it in this thing, right? So he gets that Z value. So he takes that equation, then he makes it like a little bit more complicated, right? So because with this non-ideal gas fix thing to get the Clausius-Clapeyron relationship, it's trying to find like where he releases methane or where he releases CO2 from the clathrate. So it can store hydrogen, it can store CO2, it can store methane, it can store I think those are the main things that you store in it. And it can also be used to like separate. So if you have a stream with methane in it and propane, and you want to separate out the methane, you can use a clathrate to separate just the methane. So it can identify certain components of the gas and like pull them out into a solid crystal. Right. So then it can store it, or you can also like separate. So there's a few uses for clathrates like that. Anyway, so this thing uses something called the Henry's law constant, this HS. Okay, so the original Clausius-Clapeyron has this enthalpy of vaporization in it, right? So get the vapor pressure per a given temperature. This thing has a Henry's law constant, which means that you have basically a mixture of two things. If you have like CO2 dissolved in water, then what's the vapor pressure? How much CO2 gas is in equilibrium with that? So Henry's law is one of the laws that's like an Arrhenius kind of function, right? So this paper is kind of interesting because he's also using Henry's law in this thing. So we got Clausius-Clapeyron last time, and it's basically got this log of something which is 1/t, and the slope of it's going to be some like energy or enthalpy, right? A straight line. So that's Arrhenius. That's going to be either like Arrhenius behavior, or it's going to be Irene rate theory for chemical reaction constant, right? So basically it's the same functional form, like some energy over KT gives you like a probability that something's going to happen. So it's like an activation energy. So you have some barrier for something to happen, it has to get over that hump, that height of the hump that it has to go through. So that B, and the amount of the stuff, the probability of it happening, of the viscosity, is going to be equal to that times some constant. It would be like the zero viscosity for some reference temperature. Right, so this kind of exponential behavior is like all over the place. Like we'll see this again with the Boltzmann distribution for atomic energies, for electrons. So it'll be the basis for calculating the heat capacity. So this Clausius-Clapeyron kind of looking thing occurs like over and over and over again. Like you're always going to have log of something versus 1/t. The slope is always going to be the energy, right? And this means you have an exponential dependence on something. It's just like the Boltzmann factor, like to get the probability of something happening, like exponential of the energy over the KT is going to give you the probability of something would happen that takes energy to happen. Right. So that's like the standard. There's various ways to drive it. Basically, you should know that functional form. It shouldn't be something unfamiliar to you. Like whenever you see log of something or 1/t, you should be in happy land. That should be your ground zero. You're happy there. It's a straight line. The slope of it is the energy of the thing happening divided by R. Right. So you have to kind of get familiar with that because it's over and over and over and over again. And I'm showing that it's in completely different frameworks. Like Clausius-Clapeyron has to do with vapor pressure of liquids. Arrhenius is going to be like viscosity is described as an Arrhenius function, like the WLF function for polymers is basically an Arrhenius function to describe the viscosity of polymers. And it's also going to give you a log of viscosity versus 1/t dependence. And then for chemical reactions or metallurgical reactions, you can use this Irene rate theory, which is the same function, except it's talking about a chemical reaction. Then the Irene rate theory is kind of borrowed to get to the Henry's law constant, which has to do if you're dealing with environmental, you have like a dilute amount of pollutant or something in water. You want to know what amount of that is going to go up into the air. Right. So if you're cleaning out a tank and it's got this stuff in it, like some sulfate thiol thing in the liquid, and you got to go into the tank, what kind of respirator do you need to go in? It's because you need to know the concentration of thiol, which is a neurotoxin and also a tetragen, and also causes cancer and all kinds of stuff, right? So everything bad. It smells bad too, but basically don't deal with thiols if you can avoid it, you know? So anyway, that's, and also they're using, so he's using kind of a thiol in this paper. He's using thiophene, which is, thiophene is, and that's the magic foo-foo dust that makes the clathrate work. It's this thing like S, like that, and then that's THF, tetrahydrofuran, and this is thiophene. So and THF is also a magic foo-foo dust for clathrate. So you throw it in, like your normal transition is going, like the methane clathrates that are at the bottom of the ocean that are going to cause the end of the earth when the temperature rises 1 degree of the ocean, right? Just release all that greenhouse gas. So that it can change the transition of that thing by like 100 degrees C, like huge amount. So if you can stuff some thiophene into the ocean, it's going to kill all the fish, being a neurotoxin, but basically it's going to save the earth because it'll keep the clathrates happy. You know, so there's kind of a balance we have to make, you know, once we're down the road of CO2. But anyway, so those are two of the magic chemicals that somehow make clathrates work. Make us like control clathrates. Anyway, so you'd want to know like how much of that stuff is going to go into the vapor phase. So then you'd have to use Henry's law constant, which is it's someplace here. It's in the new version. I put a bunch of things on this. It's too bad that it didn't do it for me. But anyway, this is a paper from like 2020 looking at basically Henry's law constant for gas absorption on a surface. So basically when you have, it says two rules of and this chapter is single component, and this stuff we'll talk about later with, because it's multi-component. You have water and you have some kind of thiol in it, and it's going to vaporize. You need to know what the concentration is. So you dilute. It's not like 50% thiol. It's just like parts per million. You want to know how much goes into the vapor phase. In that case, the escape from the liquid to the vapor is like a chemical reaction. So you just take the Van Hoff equation, which looks exactly like the Clausius-Clapeyron, and also gives you log the reaction constant versus 1/T. It's a plot, and the slope of it, again, is going to be an energy or an enthalpy. Right here is the enthalpy of reaction that comes out of the Van Hoff equation. But it's also just going to be log versus 1/T. Slope is the energy. Same thing. Right? So anyway, Henry's law takes that idea, and the escape of the thing from the solution is going to be like a chemical reaction. Like there's going to be an enthalpy associated with it. So they just take Van Hoff and they call it Henry's law. For when you deal with, like, environmental engineers do that quite a bit. But anyway, that versus the normal situation, which is called Raoult's law. Okay, so I just mentioned that here because we'll talk about Raoult's law in another chapter. But so in the Raoult's law, you have like the concentration in solution, like the mole fraction, and then you have the saturation pressure that you get from Clausius-Clapeyron equation, and then you have the vapor pressure that you have. So you have your water, and you put ethanol in it. It's probably not a good example because there's a large enthalpy connection with those two. Like the volume, actually, when you make vodka, the volume of the system drops. It actually has a change in volume. Then that indicates there's a large. But if there's no enthalpic contribution, then the vapor pressure of ethanol above the vodka is going to be the concentration, like your 35%. Alcohol, and then the vapor pressure of alcohol will give you the pressure of the alcohol in the air above the vodka, right? So it doesn't work with vodka because those two they bind together, the polar attraction. All right, that's called Raoult's law. That's called an ideal mixing. It's an ideal mixing law for two components. Henry's law would be actually really like vodka, where you have some kind of special attraction between the two, right? Or the thiol and water. So you're not in this 50% range, you're in like parts per million range. Right. And in that case, this Raoult's law is non-ideal, it doesn't work. So then you replace the vapor pressure that you would get from Clausius-Clapeyron with something called the Henry's law constant. Then you do the same thing. You get the pressure and the vapor in the tank that you're going to have to wear a respirator for from the concentration in the solution at parts per million. And then this Henry's law constant, which follows this idea, the same thing as Clausius-Clapeyron, like, or the same thing as the chemical reaction Van Hoff equation. Right? It's going to be ln of H12 minus delta H, kind of reaction divided by T squared, or yeah, well, I mean, it's going to be the change in that versus d1 over T delta H over R, right? Except this thing isn't the saturated vapor pressure, it's this Henry's law constant. That's the idea. So it's pretty confusing, but it shouldn't be that confusing. They're all log something versus 1 over T, you get an energy for the slope. It's a straight line. You see it over and over, and the framework changes. I think the easiest thing is just to think about it in terms of like an escape energy. And it always is something like an escape, like, well, the chemical reaction, you're kind of escaping from one state to another state in the chemical reaction. You know, the chemical reaction constant, this K equilibrium is going to be the product concentrations over the reactant concentrations, because it's like Y over X, something like that. So it's basically the reactants multiplied together concentration. So we'll talk about that a little bit later, but so the Henry's law looks a little bit like that if you work it out. But anyway, so that is involved in this paper too. So there's a lot. Like I said, I think I mentioned to somebody, so there isn't like a paper that has just one subject in it. It's got everything together. Right. So we'll look at these things later, but you have to kind of get a glimpse of them now. And then this thing, so anyway, it asks you to derive this equation. So basically, it's solving some of the problems with this. So one problem is, one assumption of the Clausius-Clapeyron is it's an ideal, right? So it is an ideal, so you put in Z, you put in the compressibility factor. That takes care of non-ideal gas, right? It's got excluded volume, it's got attraction that makes a liquid state. This Z takes care of that, right? It's kind of a fix for that. So that's the first step you'd want to do to fix the Clausius-Clapeyron, to use it with the Claythrates to see when it's going to release the methane from the ocean floor. Right. So anyway, so there's other problems, like, in other words, because it's not a Raoult's law ideal mixture. In other words, the Claythrate is definitely not an ideal mixture. Like, you don't have marbles, red and blue, mixed together in a box and you shake it up, because there actually are little claws that are holding onto the methane molecules, right? And that is not marbles in a box. So this Henry's law constant accommodates that it's not an ideal mixture. So you're talking about escaping from a claw into the vapor phase. There's going to be an energy associated with that, like a chemical reaction. In fact, it's basically a chemical reaction. The claw has to open and let the thing out, right? So that you need a Henry's law constant for that claw. Luckily, someone's figured out and again, a power series expansion into how you would get that number. Right, so everything is like empirical when you start seeing these power series expansions, like a number, then 1 over T, 1 over T squared, 1 over T cubed. So it's just like fit the data and get the numbers, and you can predict it. Right, you can fit anything with a power series. Is the kind of religion of this thing, right? So, and you can, so it works pretty good. Most of the world is based on equations like that, like how your car, in the modern cars, like a lot of steering and the brakes aren't actually attached to anything. They're just computer wires going to some motor that does something. It's like the idea that you turn the car and it turns is based on an equation like this. Right? So everything in your life that you're relying on is based on power series expansions of things that predict what the performance is going to be good enough that you don't hit the dog or whatever. So anyway, so that's kind of, these things work, even though so no, this isn't the truth, but it's good enough for almost anything you want to do. So that's the idea, right? So some things are the truth, like Clausius-Clapeyron, ideal gas, those are true for under the conditions that they're given. And then you have to go and figure out how you're going to make it into the real world. And this is a pretty good example of, I do that. Step 1, use Z, which is van der Waals. Step 2, well, it's a claw, it isn't an ideal solution. You have to use Henry's law to modify that energy. Then number 3 is this mess down here, which has gone through. I think it goes through it in this paper, the second reference paper. So he goes through like how to get this thing. Like, in fact, the same equation is right here, right? And he kind of goes through step by step how to get that. So in order to do this homework, if you want to do it decently, you have to kind of look up this. I mean, I've given you these references. There's some that I didn't give you, you can look up if you want. But basically, you're gonna have to kind of figure out how this all fits together. Like derive equation 3 means you have to look at the paper and figure out how to do it. I mean, kind of piece it together yourself. Basically, you feel a lot more comfortable if you go to the paper where he actually derived it. Just kind of parrot whatever he said. Let's see what else is in here. So the assumptions of the Clausius-Clapeyron ideal gas, and then you make this assumption that the liquid and vapor states, the vapor, there was a delta V is just the vapor. And forget about the liquid volume. Those are the 2 assumptions to get to the Clausius-Clapeyron. And they're definitely not valid here. So then that's why he has to fix the equation, right? Because it's not an ideal gas. It's not whatever. I don't think either one is really valid here. 2, the Z, that's just what I did. And then Ping-Robeson, so it asks you what this thing is, this Ping-Robeson. So that's gone through. So this chapter gets to that at some point next week, probably. But so the van der Waals, I tried to give you an idea what it is. So there's different, in other words, since the ideal gas doesn't work, there's ways to fish it around. So one is do a Taylor series expansion and density. So you have Z is this equation, and then just say, well, that's going to be a Taylor series, and I can pick out these terms. Right, so that's called a viral equation of state. And that's like that's one of the basic equations of state. So that's just a brute force kind of have these parameters, right? The A term would be like the ideal term, and then these other terms are going to be modifications to it, right? Kind of binary modification, ternary modification. So there's kind of logic behind it in the sense that people have forced on it. Basically, it's just an empirical approach to it. So then we don't need that right now. All right, so this is kind of good to see. So you have, this is the ideal gas law. So P goes with 1 over V. So 1 over V, if you plot it, looks like this. It's just like a swooping curve. Right, so if you plotted P versus 1 over V, it would be a straight line. If you plot P versus V, this is log V. This thing swoops down. Right, so that's what an ideal gas. So if you look at water and you start decreasing the density, so you increase the specific volume, and the pressure, so you get the pressure dependence at low density for these are, each one is an isotherm, right? So you have 100 degrees, 200, 300, 400, 500. So basically, this is starting 500 is like almost like supercritical steam, right? So, but basically that curve at the high temperature and low volume is following the same shape as an ideal gas, right? You have this kind of 1 over V dependence. And then as you cool it down, this other behavior shows up that isn't anything like an ideal gas, right? So over here, it's incompressible. So you increase the pressure, the volume doesn't change at all. So it's a straight line up and down. That's a liquid, incompressible liquid, right? So they'll have a straight up and down line. So this is a liquid phase in the dense state, and it's a vapor phase over here. And in between, this is like no man's land where you have 2 phases that are in equilibrium with each other, a liquid and a vapor, right? And as you increase the temperature, you reach a point where those disappear, and you just have this kind of kink in the curve, right? There's like a kink curve, right? So the point of having these more complicated equations in this PV equals RT is to predict those curves. Like, so in order to get this kink in the curve, you need to include excluded volume. So the van der Waals parameters, you need the excluded volume, and an attractive potential allows you to form a liquid state, because the ideal gas will never form a liquid state because it has no attraction. In fact, it can't, the atoms can't even see each other at all. They just pass through each other, right? So you need to modify this equation to accommodate to get a real system out of this, right? So anyway, so that's where the advent of these other, we don't need that right now. So this is kind of like a pile of different, this is the van der Waals equation of states. They have excluded volume, this attractive potential will allow you to get liquid state, and it's a binary interaction, so it's squared density. One of a specific volumes of density squared. Right, so A times rho squared. That's kind of what that is. Right? And then if you put this all in terms of rho instead of volume, then you get this expression that looks kind of weird, but that can be rearranged into a viral form. This B, C, D, rho, whatever. Right? In that case, these terms, so the B term, the second viral coefficient. So the first viral coefficient is 1, the second one is B. That's called the second viral coefficient. If you just take the first two terms of this expansion, that thing, and then use the van der Waals, you get this expression, which says that the B is essentially the excluded volume. Right, so the B is going to have units of volume. It's the excluded volume, because B, volume minus B. Right, so the second viral term is basically the volume, the excluded volume for this, whatever molecule it is. Then it's excluded volume modified by the attraction. So A has units of energy, because A would be PV, right? And then it's also got units of volume. So it ends up with units of volume and then energy. So you need to normalize it kind of by RT. So basically A by RT is going to have units of volume, but it's a volume of attraction that depletes the excluded volume. So you have your solid object, it can't pass through it, but there's something else going on, like it can make a liquid state, so they have to be able to cluster by attraction. So that attraction makes it look like it has a smaller volume than it actually has. And so the second viral coefficient is the modified excluded volume that accounts for this attractive interaction, allows you to have a liquid state. And you notice that attraction changes with temperature. So the higher the temperature, the attraction gets smaller. So it's just going to make a vapor. It's going to act like it has no volume. So you can set this to 0, and you could find a magic temperature where you'd get phase equilibrium. In other words, it's going to be liquid, and it's going to, this excluded volume will disappear. It'll act ideal when B equals A by RT. Or when the temperature, when you reach a magic temperature where you have a ratio of A by B with R in it, right? So the magic temperature is going to be A by BR, basically. Right? That's your critical temperature. So by combining a model with this empirical expansion, you can figure out what the magic temperature is, the phase separation temperature, critical temperature. So this is just the engineering expansion. Take the first two terms. This is a model for what something, the simplest possible model, and then just solve for what B is. You find out, you can solve that, set that to 0, and get a critical temperature. So that's like the simplest thing that you can. All right, so you can put in the critical temperature. So if you want to get like a universal A and B, you can plug in here, but this equation will work at the critical temperature, the point where the phase diagram reaches this critical point, right? So you have ideal gas behavior, then this weird hump thing, then there's a point where liquid and vapor become the same thing. So you have supercritical. So I should show you what that looks like. There is a video for everything. Let's see. Somewhere in here. It was actually up here, right? That's not super cooled. It's down here. Thermal C. Super cooled. Supercritical video. So this guy
It's time to improve your writing game with Grammarly Go. Grammarly Go is an AI service that
Every substance has a critical temperature and a
listen to the German guy. He shows it right here. And the first thing he shows, he's increasing the temperature and he goes through the critical point. So below the critical point, he's got liquid and vapor and equilibria. It's a sealed. So all he does is take, you can buy dry ice, right? CO2, solid CO2, make this pressure cell, stuff it full of dry ice, and then just heat it up. It'll melt and make liquid CO2 with vapor CO2. And you can just heat it up enough and get to the critical point and it disappears. Like anybody could do this, including the German guy. I don't know if I can zip through. I don't really like to hear him talk. I don't like his glasses are weird. Can you imagine this guy in a bar is what I keep thinking about? I don't know why, but he's got this, because Germans always go to bars. They'll always be like drinking at a bar. I don't exactly see how it's going to work with him. Anyway, so he just stuffs the CO2 into the cell and then he just heats it up. The temperature's going up and then boom, it disappears. That's the theme of this.
and temperature reach the critical point, the distinction between the liquid and gaseous carbon dioxide becomes less visible and eventually disappears.
I mean, it's pretty cool. So at that point, it becomes, it's got
The phase boundary between the liquid
but it's got the solvation capability of a liquid. So you can dissolve things in this like polymers, and but it's got the viscosity of a gas. So it's pretty weird. Like you can do special things with it. I mean, the main thing people use it for is separating caffeine from coffee. Then you can make coffee that doesn't have cyclohexane in it that causes cancer. Right? Then decaf coffee. Right. So you can also, I mean, you can extract a lot of different kinds of drugs from plants this way, you know, with CO2, because it's kind of polar and it can pull off the stuff. And then when you dry it, the CO2 just goes off in gas and then just pure whatever drug you want from it. You know, so I mean, a lot of the I don't know, the things you buy on Amazon, you know, made that way. It's better than using cyclohexane or some other solvent. That's one thing. What's the other thing? Oh yeah, I mentioned the other day superheating. I noticed that I didn't show you this thing. Super cool tricks or whatever. Music. So basically you just take a bottle of water. You have to be careful not to whack it. So you just fill it up, put it in the freezer and let it sit there for, he says, like 3 hours or something. And then you have super cooled water. It's liquid, but it's below the fusion. If you just whack it, it turns into crystal. That's one thing you can do. There's a bunch of tricks you can do. You can put food coloring in it, do the same thing. You can take a cold cherry or something he's using. Oh yeah, you can just pour it on a dish and it'll crystallize. Like it's liquid, super cool liquid, and it just wants to crystallize, but it hasn't reached that point. But once it gets any kind of nucleating agent, it just crystallizes immediately. So you can make like a pile of stuff with it, ice. And if you take a cold, a fruit that's also like below freezing, it's a nucleation site. So just will nucleate all the water on it. Makes these like weird fruit things. I guess you could use it if it didn't melt. You know, you could use it to as an hors d'oeuvre or something. I guess, but it's pretty cool. You know, probably worth trying if you got extra time. But anyway, this super cold exists. The other thing is cool is like you keep talking about like to get the dq is ds by t, it has to be a reversible process. And you say like nothing's reversible, right? So, but some things are reversible. So this thing kind of shows, there's a bunch of these on the internet. This is called laminar flow, which is reversible. and it's hard to believe that it's reversible. Let me see if I can make this larger somehow. Doesn't seem like it wants to. Like here. Oh yeah, that's bigger. Okay, so he just puts, he's got glycerol, and he's got 2 cylinders, and he puts the drops of glycerol in, and then it looks like it's not reversible, like it's mixed, right? But you can unspin it, and because it's laminar flow, it's like deck of cards flow. You can actually totally reverse the thing exactly back to what you started with, except for the gradients. The gradients are against reversibility, so there's diffusion gradient that happens in it. Right, there's a bunch of these on the internet that show kind of laminar flow as an example of reversible process. Anyway, that's another thing I saw that I didn't show you before. But so what are you doing? Let me go back over here. So that was just to show this critical point. And then yeah, so once you get this defined in terms of the critical temperatures, and you can solve. That's why in that program you put in the critical. So one of the things you put in the program is like the critical temperature pressure, and the thing called the eccentric factor of it. So for each material, if you put those in, then you can get this kind of universal, like all the curves start to look the same for the phase diagrams, right? So if you can center them on that critical temperature and include one fudge factor called the eccentric factor, and then you can predict the whole phase curves, can predict all these curves. So what those look like is this: like if you calculate, if you take that free energy, if you write a free energy expression based on that, when you set it equal to 0, it'll have 3 roots because it's a cubic equation, has 3 roots. So it'll look like this. When you're in this region of the 2-phase region, it's got 3 roots. So it's got like 1. So the 0 point is where the circles are. There's a root in the middle, and there's 2 other roots. So the 1 root is at low volume. So that's the liquid. The other one's the high specific volume. That's a vapor. And those 2 are in equilibrium with each other because they have the same derivative. Something about the area under this hump and the area under that hump are equal to each other. So because of that, those 2 points are equal to each other. That's called the Maxwell construction. And then as you change the temperature, that equation changes, and eventually it reaches a point where those 2 points see they're converging together, and they reach a point where it's at the critical point. And then above that, you're actually just predicting this curve. Like this curve is that curve, right? So the only part where it isn't that curve is where you're in this place where only the 2 phases can exist in equilibrium with each other, at the tie line points. So that kind of curve, solving that kind of equation is basically what that Excel sheet does. This solves it for this complicated Peng-Robeson equation. And that's what he uses in the paper too, to get the Z. So you can get the Z from that and then plug it into the Clausius Clapeyron to get the vapor pressure thing. Anyway, that's that business. Let's see, we got like 10 minutes. CalFad we can do later. We went through that already. I think we went through a lot of this stuff. Actually, we're almost done with this chapter, this section. Just a couple of little tie up the knots things. Any questions on anything? But I mean, it's kind of a lot of stuff, but the paper, you know, I think if you go through that paper, hopefully you can kind of, you know, get a feel for it by working through the stuff, and there's a few questions. There's also like, so there's a book on clathrates in here. Let's see, inside the homework, under this thing, there's like, the thing about the Earth ending is this clathrate gun hypothesis about how the gases are stored under the ocean, the temperature rises 1 degree, and all life ends. That's what is kind of a little wiki right up on that. This thing goes through, it shows some of the water structures. There's someplace, I think it's in this book though, where it's really shows So these things all, if you want to look at them, you have to put the F at the end and it'll come up theoretically. This is showing the clathrates. This is a petrochemical. It shows you what the problem is. It actually forms a crystal. Like if the pressure and temperature get wrong and you have methane gas and petrochemicals in it, and especially at deep ocean wells and things, then you get these weird pressures showing up. I mean, they're digging off Brazil. They go through 3 miles of water and I think 4 miles of sand or whatever, rock, to get to the oil in the middle of the ocean. It's insane. You know, and the pressures and the temperatures are incredible, like things unearthly. So they get things like this. They get a lot of problems with pumping the oil out of that. Clathrates is one of them. Asphaltene's another one. Like there's kind of this tar stuff that crystallizes in it too. So there's a lot of kind of engineering problems. Also is causing the end of the earth too, you know, but it's also insane, like why you would do that. I mean, money's involved, but still. Anyway, so clathrates are both, all right, so yeah, here they show, this is the place. So these are water molecules, like OH. So it's going to be the 3 of these is going to be like OHH. These are just water molecules, just clustered together in this structure. That's what these crystals are made up of, just water molecules. They're all tetrahedral arrangements, and they trap these molecules inside of it, and they stabilize that crystal structure that forms. So it's actually kind of amazing that the thing is mostly water. It's just water, and it's got some organics that kind of enable it to form this fairly simple crystal structure, right? So it's believable that it could be such a problem. Like it's easy to make it, I think. Anyway, this book's, I guess if you're interested in clathrates, there's a whole book in here you can look at. Doesn't really have to do with the homework much, but it's just topical. Then these two are kind of, equation 4 is where he derives it, and equation 4 use, I think, adds something to it, just like shows a little bit about how that equation, like he also uses it. That's the same equation 4. It's just some comments about it too. So those 2 papers seem to be important to that, the last question there. I don't know. Anyway, just let me know if it's kind of a more challenging thing than last week. So if you have problems with it, just email me. I can help you through it, you know. But like if you can't figure out, it's like derived 2 equations. So some people have problems doing that. So I can tell you how to do it if you can't do it. So otherwise, I think it's, I don't know what else. This is just straightforward, like what are the assumptions? What is a cubic equation of state? So anytime you get a question like that, it's going to go back to the van der Waal. The van der Waal is the simplest thing. And there's a lot of cubic equation of state, they just add on to it. It's just adding more and more onto it to tweak it so that it fits some system, right? So there's many different systems, they all behave differently. You just add another term and basically you can get the thing to work better. That's more or less the idea. There's probably widely used like 50 different equations of state just for gases and things, right? So, and if you're in a business, like they will have their preferred equation of state. So, like if you're working for some petrochemical company or something, TPG or whatever, they have an equation of state internal. That's their like secret equation of state that works for their stuff. So besides the 50 that exist in books, there's probably another couple hundred, you know, that people use. So anyway, the Ping-Robeson one is one that's everybody uses. Like you'll see it in a lot of papers. And then the van der Waals is the one that you can make sense of. So that's about it, I guess. It's a lot of stuff like if you can figure out what Henry's law is, why you would use it, why he's using it here, and then what Raoult's law is and how they relate together and how it goes back to this compressibility factor and van der Waals. You can put all that stuff together, like you're in pretty good shape. You know, you can read a lot of different papers, I think. So it's just like, you can see this like one paper can lead like a window to a bunch of different stuff, but it all comes back you'll see like people using this over and over again. And you'll see these plots of log of something versus 1/t everywhere, you know, so you have to be able to say like, I'm really comfortable with that. And I know what the slope is going to be in energy, and then go back from that and figure out where they're coming from in the paper, you know. Anyway, why don't we quit there, I guess, unless there's questions or anything. All right, so have a good weekend. Try to get this thing done. Oh yeah, it's a long weekend too, yeah, except this class, it doesn't matter. Okay?
Steve, I'm thinking about 4 points. I'm gonna you thinking on the red laws, a question, and really, like in general.
Okay, so, well, yeah, because we haven't, all right, this is jumping ahead because it's for a mixture of things, and this chapter is really a single thing, right?
Yeah.
So that's what the problem is. So we haven't talked about mixtures of things. So, but basically, in a mixture of things, if it acts ideally, so in other words, it acts like marbles. So you take like red and blue marbles, shake them up, and then mix. Right, so that would be like an ideal mixture. Right, so there's no like special attraction between blue marbles or red marbles. Right, so basically, that's what Raoult's law describes. And there's nothing, if the red one wants to escape from it and make a vapor, the blue one wants to escape, there's no special thing holding it in. There's no affinity of the red to stay.
Oh, you don't know yet? What do you mean?
It's just probability of whether it's in gas or liquid phase. It could be in either one to flip a coin.
Yes.
Right, so it isn't, if it's not an ideal solution, then it prefers to be in the liquid or it prefers to be in the gas. Right, it could be repelled from the liquid or it could be attracted to the liquid. Right, so it could be some kind of enthalpic, and no, it's just entropy that's driving it. It's not an enthalpic thing that's driving it. So ideal means there's no enthalpy, it's just entropy, just randomness, like things fly out, things fly back in, so probability. Right, so that's what Raoult's law talks about. No, there's a probability that the gas atoms going to jump into the vapor is proportional to how many gas atoms there are in the liquid.
Okay, that's confusing.
Like how many blue marbles are in the mixture of red and blue marbles. The number of blues that are in the gas phase is going to be proportional to that.
Yeah.
So the gas vapor is going to be but if you have an attraction for it to be in the liquid, the vapor will have fewer of them because they want to be in the liquid. There's an enthalpic interaction, then you'd have to use Henry's law. So Raoult's law is for the case where there's nothing holding it there. It's just entropy. It's like random. And Henry's law is if there's actually an attraction holding it in. That's the idea. So Henry's law is like a chemical reaction, so it's going to follow that Van Hoff equation. We talked about the probability, and Raoult's law just depends on the vapor pressure. Like just what is the vapor pressure of that phase times how much of the phase has been there. There's how many blue marbles, and the vapor pressure of the blue marbles alone gives you the pressure of the blue marbles above the red blue mixture.
So for Henry's law, he went over that a little bit, but I couldn't see your handwriting.
That's all right.
So I was like, and I was trying to find it on the notes things, which I eventually did. It took me a little second.
Okay.
Yeah, it took me a little second to find.
Some of this stuff, I think just Google it, and the wiki page helps and stuff.
It was hidden very well, and I was like, how did I find this the first time? And I was trying to think to myself, like, I found this several times.
I've been there.
I couldn't find it this time. But so for Henry's law, you were saying
Henry's law is it's got an attraction, so it isn't this business of probability, it's a business of like a chemical reaction. Like with the clay plates, there actually is a claw that holds the methane in, and that claw has to open to let the methane out. And that involves a chemical reaction, like an enthalpy of reaction. Right. So it behaves just like as if you had a chemical reaction of A plus B goes to AB. And there's a rate constant, it's like concentration of AB divided by concentration of A and B. Right. So gotta quit.